All right, welcome to Objective 6.5. So we're going to continue on with this. And so now we're going to be looking at the different norths that are used on a map. Believe it or not, there are actually 3 norths that we use in mapping and in geomatics. And every single one of these have their purpose and the reason why we use them and how we move between them. And you'll see this on every topographic map as well. You'll see all 3 norths so that you'll be able to identify which one you use. So the 3 norths are the true north, the grid north, and the magnetic north. So the true north is the rotational axis of the Earth. That's where it's located. And so it is it's considered static for the most part. I mean, it does move according to geodesy, but we just consider it static. And so therefore, it's a good fixed location. It's where all the lines of longitude converge. So mathematically, though, it is very hard to calculate with because everything is curvilinear. But we still use it as a major reference so that we can go back to it and be like, okay, that is where it is based on latitude and longitude. Then we have grid north, and the grid north is straight up on the paper. That's all it is. So if you look at your maps, you're going to see that, for example, the UTM grid, which I will be getting to next module, goes straight up. And it doesn't curve, it doesn't do anything like that. And that's because with a grid north, it is forced to be flat on the paper. So therefore, it is very easy to use with measurements and easy to do calculations with. So it is also considered static for the map. So if you get another map, you're going to see grid north is going to be a little bit different again. So it just depends on the map, and that's why we have to talk about these 3 norths, because every map should have these. The last one is magnetic north, and this is that magnetic North Pole. And so this one changes a lot. And right now it's kind of on a big race to head over to Russia. It used to be in the Canadian Arctic. So this one will change annually. It changes daily. It has random changes, and it has what we call secular variations. So the secular variations is what we take. It's kind of like the bigger picture of the movement. And so when we create a map, we'll often use secular variations for the description of, okay, that it is changing, 12 minutes per year. And so that allows us to kind of take that bigger overall view of that magnetic north and make it into smaller chunks as it goes through. So we can do an easy calculation with it. Annual changes, they swing back and forth. It's a kind of a pendulum movement. Um, it's not a lot. Like by the time you get even down to Calgary, you hardly notice it. You're certainly not going to notice it in the on a compass. The daily variations are negligible. They move approximately like 3 feet at the most, but they are there. And so the closer you are, if you're like trying to stand on top of it and locate it, you might notice that change. But otherwise, it's so minimal by the time you get down to Calgary or even further south. There are random changes. Now, the random changes are really kind of cool because all it takes is like a cyclone in the Arctic and it causes it to move. So like big snowstorms or even earthquakes or volcanic eruptions, all of that cause the magnetic north to change randomly, and then it'll go back and stabilize. So it is a factor that we have in the changes of the magnetic north. And so just kind of keep that in mind as you go. So here it is a picture on the side here showing this is the south. It's showing the South Pole, but it's the magnetic North Pole, right? Because that's how magnets work. So we have our magnetic field that's going around the Earth, and then we have the one location where everything kind of connects. And then we have a difference between the geographic North Pole, which is the true north, and the magnetic north. So that's what's happening there. So we go here, this is what you're going to see on a map. And these are almost the symbols that you would see in if you were to be doing the map itself. So we have true north, which is this arrow. It's always represented as an arrow. Then we have the grid north, which is normally represented by a box. So you'll see a little square box, a grid that's on top of it. The magnetic north pole, actually, the true north is often actually represented with a star. On the Canadian NTS sheets, true north is actually a star, not an arrow, because the magnetic north is actually half an arrow. So to prevent any confusion with that, that's how it's usually represented. Sorry, I was looking at an arrow on this picture, and then I said the arrow. So true north is a star. If it helps you remember, true north is where Santa Claus lives, and that's where the tree, where the Christmas tree puts a star on top. So if that helps, it's a true north. And maybe Santa is true in your life, and that's fine too. So, and then we have grid north. Grid is always the rectangle square, and magnetic north is half an arrow, so it looks kind of like the needle when you're looking at a compass. So we have a few angles here that we could talk about, and there's a little bit of different variation with the way that the words are stated, so I'm going to give you examples here. So the magnetic declination goes from true north to magnetic north. It doesn't matter where the grid north is at all, okay? So if the grid north is right smack in the middle, it's still the magnetic north going from true north to magnetic north. The magnetic declination going from true north to magnetic north. Then we have the grid convergence, which is going between true north and grid north. The grid convergence, or also known as the convergence angle, I'll refer to it as a convergence angle. This one doesn't change. It is always stable. Magnetic declination is changing because the magnetic north is changing. True north and grid north are always stable, so that this convergence angle always stays the same in our maps. Then we have the grid magnetic north or magnetic angle. So this grid magnetic angle I call the grid declination. Okay, so the grid declination and I've mentioned it down here, goes from the grid north to magnetic north. This one changes as well because it does rely on the magnetic north. Okay, so the grid declination or the grid magnetic angle, the magnetic declination, which is still the magnetic declination, both of those change. The only one that stays the same is the grid convergence because of not having to rely on the magnetic north. So these are the three norths that we're going to be using to calculate between. This next objective is a little bit more challenging when it comes to conceptualizing what is going on, but we'll spend quite a bit of time trying to figure this out and work through it.